This is Daniel Coosbury, and in this video we're going to look at how to construct a confidence interval for the population mean when you don't know what sigma is. So we're changing the situation a little bit from a previous video. So I made one where you do know what sigma is, and this one we don't know what sigma is, and this is kind of a more realistic situation. So in other words, let's imagine that we have a population and we don't know what the mean is. And most of the time, if this is true, then we don't know what the population standard deviation is either. It's very unusual to not know this but know this. So let's just assume we just don't know anything about the population. And so what we do is we take a sample from the population, and we can find things in this sample like X bar, which is a really good point estimate for the mean, the population mean. I'm sorry, for the, yeah, so if we're asked like kind of what's your best guess at what mu is, you take a sample and say it's X bar. Now, of course, we know X bar is random and it can bounce around based on what different samples. You could get different X bars. And so we don't want to just use a point estimate. We want to make an interval. And so in a previous video, we learned how to make confidence intervals for the mean if we knew what sigma was. But in this case now, we don't know what sigma is, so we're going to need to estimate sigma using our old friend, the sample standard deviation. So what we're going to do is we're going to use S as a stand-in for sigma, and it's going to have to change the method for how we construct the confidence interval. So the probability theory changes once you don't use this and you start estimating for sigma. Instead of using standard normal, we're going to have to use what's called the t-distribution. So the student's t-distribution is a nice bell-shaped unimodal curve. It's a continuous distribution. It's nice because the mean is equal to 0, and it looks a lot like the standard normal curve, because the mean is 0 and it's kind of bell-shaped. So if you look at this, the standard normal is this black curve, and these are different versions of the t-distribution. So the t-distribution changes a little bit based on what are called degrees of freedom, and they determine what kind of t-distribution you get. Kind of like with the normal, you had the mean and the standard deviation determine what kind of normal distribution it was. The degrees of freedom are going to determine what kind of t-distribution you get. So you can look at this. I need to be able to spell distribution. You can look at this picture and see you change the degrees of freedom, you get different pictures. But the nice thing is they all look like normal curves, which makes the t-distribution really useful. So it's very close to the normal distribution, which is why we can use it. We use it when we use S instead of sigma. You can kind of look at this. So this is kind of the results that correspond to the central limit theorem for X bar. So this should look familiar. Since we know X bar is random, if the central limit theorem conditions are satisfied, meaning you have a normal population or you have n's bigger than 30, then we know X bar is a random variable with the normal distribution with the mean this and standard deviation that. Now it turns out when you do a little bit of subtracting and dividing, if you find the z-score of this by subtracting the mean and dividing by the standard deviation, you get something that's standard normal. So in other words, imagine taking this, subtract the mean, divide by the standard deviation, which is what's going on here. You get a standard normal, which has mean 0 and standard deviation 1. So when we know what sigma is, we can do all this stuff. We use the standard normal critical values for a confidence interval. So that's what we do when we know what sigma is. When we don't know what sigma is, we have to use S instead of sigma. It changes the central limit theorem result a little bit. So we have the same conditions, which I didn't write down. I think it's on a later slide. That we need a normal population or the sample bigger than 30. And then we're going to find what we're going to call T instead of Z. Let's take X bar, subtract the mean, kind of like over here, then divide by S over the square root of n rather than sigma over the square root of n. And we get something that follows the t-distribution. Let's see if I can spell. With with what we're going to call n minus 1 degrees of freedom. In other words, when you subtract the mean, divide by s over square root of n, you don't have something standard normal anymore. You have something that follows the t-distribution. And the t-distribution is defined by the degrees of freedom, which is simply n minus 1. So if you take a sample of size 50, then 50 goes there. The degrees of freedom is 50 minus 1, or 49. So you need to know this number in order to do stuff with the t-distribution, kind of like you need to know the mean and the standard deviation to do something with normal. But the degrees of freedom is easy to find. You take your sample size n and subtract 1. So if your sample is 100, your degrees of freedom is 99. So because of this, when we have to use S instead of sigma, we don't know what sigma is, we'll use S. We're going to use the t-distribution critical values, and we'll denote them like this. So this is new notation. It's the critical values for the t-distribution that we're going to use for the confidence interval. Okay, so the t-distribution critical values, they work like theoretically the same as that with the standard normal. Here's a t-distribution curve where it looks like normal, the mean is 0, and we're going to call these t's now instead of z's. But the t sub alpha over 2 has the same meaning that the area to the right of alpha, the area to the right of this value is equal to alpha over 2. So if we want to capture like the middle 90% or 95%, we can kind of divide alpha by 2, just kind of like we did with the standard normal. So this has the same meaning. This means the area under the curve to the right of this is equal to alpha over 2. Now I want to introduce you to the t-distribution table, which is table A3. The t-distribution table looks a little bit different. I'm going to go ahead and show you the big one in the back of your textbook. So it looks kind of like this. And unlike the normal distribution table, this gives you a picture where you see t down here, and the area above it is shaded. Whereas if you look back at the normal distribution table, it's the area below it that's shaded. See the area below that shaded? The t-distribution is designed so that you can use it just for this confidence interval stuff and a few other things. But the area above it is shaded, which means that the row will tell you what's the area in the right tail, the area above t, and the rows will tell you the degrees of freedom. So if I have like a sample of 20, then 19 is my degrees of freedom, for instance. So if you know what your area above is, which could be 0.05 or 0.025, you know your degrees of freedom, I can tell you the value of t on this that will give you that. So I'll just show you how to use that in an example right here. Suppose we have a simple random sample of size 10 is drawn from a normal population. We want to find the critical value for a 95% confidence interval. So if we're doing 95% confidence, so this is our 1 minus alpha, that means alpha is equal to 0.05, which means alpha over 2 is 0.025. So we're looking for t sub alpha over 2, which is t.025, which means that on our t distribution, t sub 0.025 is the number for which the area to the right under the curve is equal to 0.025. So that notation means the same thing as the standard normal. The difference then comes to the graph, because the table. The table gives you the area in the right tail as columns and the degrees of freedom as the row headings. So if I've got a sample of size 10, that means my degrees of freedom is 10 minus 1, which is 9. I'm going to go to the 9 row here because degrees of freedom, 1 minus the sample size. And then I've got the area of the right tail in the right tail as my column headers, and I know that to be 0.025. I got that from dividing alpha by 2 and getting that. So my area in the right to the right tail is 0.025, which gives me this number as my critical value. So this table might be a little easier to use because you put in alpha over 2 here. So maybe this is a way to think of this. This is equal to alpha over 2. And this is equal to my degrees of freedom, which is n minus 1. You take those two things and find the table entry, and that's your answer. So my t sub alpha over 2 is 2.262. That's my answer. That's how you find the critical values using the table. Now, if you have a newer TI-84, you have a special function in your calculator called inverse t. It's found not far from where the inverse norm function is. If you have an 83 or an older 84, you don't have this, and sorry, I don't have much for you. You're going to have to use the table. But if you have a newer calculator, you have something called an inverse t function that takes the area to the left as the input, first input, and your degrees of freedom as the second input. So in this context, my area to the left is the opposite of this, which is 0.975. It's always area to the left in the calculator. But the opposite of this is 0.975. My degrees of freedom is 9. You do that in the calculator, you should get the 2.262. So I'll show you real quick. If I go to second vars, inverse t, my area to the left is 0.975. My degrees of freedom is 6. I'm sorry, my degrees of freedom is 9. 10 minus 1. Paste, I get 2.262. So that's how you can do that in the calculator if you have a calculator that you can do it. If you have an 83 or an older 84, you're going to have to use this table. Sorry, the table is designed to be easy to use. So if you think of the column headers as alpha over 2 and the row headers as their degrees of freedom, n minus 1, it's supposed to be easy to use. You just kind of go look here. That also tells you the confidence level at the bottom, which is helpful. Okay, so now that we can find critical values, I can give you how to find a confidence interval from U when you don't know what sigma is. So this is the whole spiel. If the CLT conditions are met, which are we have a normally distributed population or n is greater than 30, then a 100 times 1 minus alpha % confidence interval for mu when sigma is not known is given by this formula here. So we're going to take x bar as your point estimate. Again. And you're going to take this as your margin of error. Where this is easy to find, this is easy to find, this is easy to find, and this is the critical value you got to look for. So when you have a sample, you're going to know your sample size. You can find your sample mean and your sample standard deviation. Just do the one variable stat thing. And then the critical value is going to be the harder thing to find. And you do it like I showed you in the last example. Use that table A3. So this is how you find the confidence intervals when you don't know what sigma is. So in another video, I'll give you some examples of how to do it, confidence intervals in this new